Center of mass is an interesting concept. All of the physics we've been doing has been tracking the location of the center of mass and how it moves. So when we've been working with projectiles, no matter what shape they are, rulers, footballs, spheres, the motion of a parabola is that tracked by the object's center of mass. So when you throw a ruler, the ruler itself might rotate around its axis. So as the ruler flies through the air, you might see it move like this and around like this. But the path that the center of mass makes is always that parabolic motion like we studied. Another example here is this rocket. So as the rocket is in a projectile, it will blast into different pieces. And all of those pieces, if you add their center of mass positions together, will continue to track that projectile, even though there is no piece actually moving in that projectile path any longer. How do you find a center of mass? A center of mass is a weighted average. So it's a position, this is cm for center of mass, of mass values times how far they are from a given zero, all divided by the overall mass. This is the same type of idea as tests being weighted heavier than homeworks. So you have a category and the percent it's weighted, and then your grade in that category. So this is like grade, and this is the weight. Right, so center of mass is a location that's based on a weighted average. When you've been using the expression F equals ma, and you've been thinking about an m, the location of that m is the location of the center of mass of an object, right? So we've taken that for granted right now, but is important when you think about the detailed size of an object. Same thing as potential energy or kinetic energy. Each one of those equations has mass in it, and when we think about the location of that mass, like when you're getting the height value of a roller coaster cart, the m that you're using is the center of mass of the system to get the potential energy of the system. Let's think about some other ideas of center of mass in our life. Center of mass is a big component of being able to balance, because being able to balance means you have a net force and a net torque of 0. So what does that look like? Well, if you took someone's body like this, right, and their center of mass is down here, and then you had this person lean over, they could lean over, and as they lean over like this, they're going to tilt their body so that their center of mass stays above their feet, which means they're going to have to stick their butt out just a little bit so that there's some mass that goes this way and some mass that goes this way, maintaining their center of mass value above the pivot point. So whenever you lean over to pick something up, notice that you'll stick your butt out in order to compensate for your mass leaning forward and keep your center of mass above your feet. There are two ways to balance an object. You can pivot and put the pivot below the object, or, which you can see is kind of challenging, right? If I have this 2-finger pivot and trying to get my pencil to balance, it's not so easy. Or you can take that pivot and you can put it above the center of mass, like this. A pivot that is located above the center of mass is a stable system, and when you displace the center of mass, it will return right back to its original position. Unlike this location, over here, if we let go and displace our mass just a little bit, it falls out of alignment. Let's try applying the formula to a configuration of masses seen below. So I've made a ruler here, and each increment is 1 meter. So we can call this 0, we can call this 1. Okay. And so that'll allow us to have an x value for each one of our masses. We have a 1 kilogram, 3 kilogram, and 2 kilogram mass kind of resting on top of this ruler. And we want to know where the center of mass location of the system is. We're going to ignore the mass of the ruler and just consider the mass of the blobs on top of it. So we'll fill in our parts to this equation. So we'll say x center of mass is m1. The first mass we come across is a mass of 1 kilogram. It's at position 1. M is 1, x is 1. The next mass we come across is a mass of 3 kilograms. It's at location 3. And then we come across a mass of 2 kilograms out at location 5. We're going to divide that by the total mass of our system. 1 plus 3 plus 2. So that's 20/6 or 3 1/3, which means the center of our mass of our system is right around here, 3 1/3. So if you wanted to balance this, you'd have to put your finger right underneath here, this spot that equals x is 3 1/3 meters, and you'll be able to hold your system up balanced. Notice the mass on the right side and the left side of this pivot is not equal. The mass over here on this side is 2 kilograms, while the mass on this side is 4. The center of mass is a position of the weighted average of mass. It does not mean that there is equal mass on both sides of the pivot. Go ahead and switch your 0 to another location and try this problem again. So perhaps call this spot 0, 0 meters, this -1 meters, and this 1 meter, and see if you find that same location for center of mass given a different coordinate system. You should realize it doesn't matter where you label 0 as long as you're consistent within a problem. Okay, so now I have a conceptual question for you. Following this up with a conceptual question, we balance a broom, just like we were talking about balancing that system of masses below. We have the handle and we have the broom head. And we're going to balance it at a position that is called the center of mass position, right? Put our finger right here. Center of mass is also sometimes called center of gravity. They're used interchangeably. One means more mg values are being used, while the other means m, although those terms cancel out mathematically, so you get the same number either time. So let's take the system and cut it at the center of mass. So we take this side, we compare it to this side. Which side will have more mass, or will the mass of each side be equal? So left, right. I'd like you to compare the mass of the left side to the mass of the right side. Okay, I will give you a demo, but instead of using a broom, I'm actually going to use a chopstick. That'll be my long part, with a measuring cup hanging on the end. Okay, so I have a balance beam system that I'm going to set up. I have my 2 supports and a chopstick for a balance beam. Now, I have a measuring cup, a 1/4 cup measure, and that weighs a lot more than this chopstick. So I know that if I were to just put this on the edge of the chopstick and try to balance the chopstick in the very center, it wouldn't work. But if I balance at the center of mass over here, I can actually get the system to maintain balance, even though the measuring cup is so much more massive than the chopstick. Okay, let me show you. So here's my balanced system. And my question is, if I were to cut my chopstick right here, which side would have more mass? That side, it's so long, or this side here, that's so short, plus the cup? All right, so let's compare these 2 weights. The weight of to this. Well, there's really no comparison. Let me ask somebody random. Wait, which one's heavier? This one? Right here? Okay. So if we take the system and we cut it at the center of mass, we're going to end up with 2 pieces. One that looks like this, and one that looks like this. And when we compare the left side to the right side, we realize that the right side is much more massive. Because the right side has much smaller x values, so it must have much larger m values in order to pull that center of mass position towards it. The left side has larger x values and less m values, so the xm's are balanced. So if the center of mass is what we call 0, we can set it equal to the mass of the left times x of the left plus mass of the right times x of the right, all over m total. And what you'll see is m total will be multiplied by 0 if you algebraically bring it to the other side, like this. And so then your m, mass, and x values for each side kind of balance each other. The left has a little m, but a big x, while the right has a big m and a little x. So our center of mass is a position that balances the average location of the center of masses. It is not a location that splits the amount of mass equally in half.